to get into a little bit more of a real research-like application. I want to get into a molecular simulation idea and see if any of the HashCache or SqlCache things that we've been working on are usable for that, and what their limitations are. So there's a bunch of ways I interact with my notebook. One of them is I have these headlines, and this one is labeled to do, and there's a link to a readme file .here. So this is like a dashboard in my notebook, a table of contents if you want. But you might also have made tasks for yourself, and so here I'll often just use a to-do list, and there is a to-do list up here for molecular simulation, and that will take me right to that heading. So we're going to just jump right into it and get to it. And today my goal is really a very straightforward molecular simulation task. I want to use the atomic simulation environment and an effective medium theory calculator to get the lattice constant of copper. And along the way, I want to see how we can use HashCache or SqlCache probably first. We may fall back on HashCache because I'm anticipating a problem that we'll get into in another video. Okay, so the way we get a lattice constant of a metal in a molecular simulation is sort of highlighted up here in this little graphic. I'm going to make an FCC copper unit cell, and then we're going to calculate the total energy of that cell, and we're going to do that at several different volumes, and eventually we'll plot the energy versus volume, and we'll see something that is kind of roughly parabolic around the minimum, and then we need to do some analysis to find what the actual minimum is. And we'll do this for copper. I'm going to use a single metal to work out maybe a workflow that we could later also do this for palladium and platinum. Now, effective medium theory is not a particularly great level of theory for molecular simulation, but it's very fast, and I don't want to wait around all day for a density functional theory calculation to work. So we're going to use this as a way of prototyping what we need to do. Okay, so that's the goal. In words, I need to build a unit cell of copper and then use effective medium theory as the calculator, and all of that's pretty straightforward. So I'm going to go ahead and start from here. I'm going to use a function from ASC.build called bulk, and that just is a convenience function to generate the bulk unit cells. And then I'm also going to import the EMT calculator as well. So let me give this a minute to get started. And from asc.calculators.emt import EMT. So this is the calculator class. And the first thing we have to do is build the unit cell. So I can just say build copper, and this is going to use all the default options, and if I look at what happens here, it will show me an atoms object. Well, this should be bulk, I think, maybe. So this creates an atoms object. It has a unit cell, and it has a single atom in it, and we can inspect this, and we can also set a specific crystal structure or a lattice constant. So when I don't specify these details, then ASC will look it up, and it knows from its own internal database that copper is an FCC metal. And it also knows what the experimental lattice constant is, and that's what it has used to construct this. And so for this, I know that the lattice constant of copper is about 3.6. And so I can just say A equals 3.6 like this, and we'll get a different atoms object. So this is the parameter that we're going to vary over. This is what determines the volume, and we can just test out that. We can get the volume like this. If I make this 3.86, it's going to get bigger, and if I make it 3.46, it's going to get smaller. Okay, so that's the setup, and then what I need to do next is add a calculator. So an easy way to do that is just to set this attribute to EMT, and now I can also get the potential energy. Okay, and that's going to give me a number. If I make this smaller, that number goes positive, so it goes up, and if I make it bigger, it goes positive and it goes up. And so if you've done very many examples of optimization, you know the minimum is between 3.4 and 3.8, and then the question really will be where is it? Okay, so what I've just done is highlight the interactive nature of a good notebook. A Jupyter notebook would do the same thing. All of this data that we've just kind of worked out is transient, ephemeral. It's not even in my own memory anymore exactly what those results were. But this is part of the process of figuring out how am I going to write code to do this. And the next step now is to decide what is our strategy for caching this data so we don't have to run these calculations again. Remember, I could make this like a VASP calculator, and then get potential energy will take anywhere from minutes to hours or days depending on the size of the calculation and the settings, and so you definitely want to be careful that you don't rerun calculations that aren't necessary. So having done some exploratory work, I know the answer is between 3.4 and 3.8. We need to think about making a list of atoms objects and then getting the energy and volumes for each one of those, and that is going to be the first step in doing our work here. Okay, so I showed you two options in HashCache. We can either write a function and decorate it, and so then we can recover the results from our function, or we can get the data and then dump the data and get a hash that we look up data for later. So let's try, let's say from HashCache, it's going to be from pycse.hashcache. Let's try the SqlCache first, and let me just see if we can do a SqlCache.dump atoms equal atoms. And this should give me an error, I think, like right away, because the atoms object is not going to be serializable to JSON. And that should be what we see here. Data must be serializable to JSON. So this is already the first indication that that you have to be really careful thinking about what can be cached. And the problem is the atoms object is a class, and it has a lot of attributes, and those it is not a simple data class, which ORJSON knows how to serialize, but it's a fancier object that it does not know how to serialize. So that is not going to be a solution for us here. And let me add a to-do item here for another day to extend SqlCache with custom serializers. So you can provide ORJSON with a default function for serializing, and it is possible to write a function that can serialize an atoms object, but I think we'll not do that today, and we'll just use regular HashCache. So we're going to give up on interoperability and a little bit on findability, but we're going to gain the ability to store our data for reusability later. Okay, so let's try that. From pycse.hashcache, import hashcache, And let me see if I can dump that one. Spell this correctly, and that does look like it worked, and so we will certainly be able to use this. And let me just try to load it, make sure that works. As you can see, I am sort of ever a skeptic. I wrote this code, and I want to make sure it works for what I'm interested in, and you should do that too, even if you're using someone else's library. Their code may also not work as you might expect. So let me make sure I can extract the atoms and even get the potential energy from it. So, all right, great. So we can save atoms objects, and here I'm actually running an actual calculation, and that may not be what we want to do, but this kind of demonstrates the potential for round trip storing of things. That allows you to create work in one day and use it in another day, even if you have to close your notebook. Okay, so let's next step work out how to run a bunch of volumes. So if we go back up here, this is going to be basically we're going to need to create a bunch of bulks at different lattice constants and then get potential energies for them. So one way we might think about doing this, and there are many ways, so I don't know what the right answer is. One way is we could decorate a function with HashCache and have it take one argument, maybe two arguments, copper and a lattice constant, and then have that decorated and have it return, say, the atoms and the energy. Let's try that route. All right, I have to think a little bit in advance here that I probably want to eventually be able to do this for other metals. So let's decorate HashCache def, let's say get energy, and we'll say make it take a symbol and a lattice constant. And I'm going to go ahead and make a docstring for myself. And now we're going to say that atoms is equal to bulk symbol comma a. And this is not a very general function. This is really only intended for FCC metals. I could specify the crystal structure in here. If you remember, that is an option here. I could say crystal structure equals FCC. But this I'm going to add here for an FCC metal, and I don't know if I should be more specific than that. This is really a bespoke for this problem function. So if I put in here a non-FCC metal, well, the EMT calculator might not be able to do it. It can only do a handful of the late transition metals that are FCC. Let's just say for a metal EMT can use. Okay, so I'm going to leave it at that. Let's say A equals A, because I need to use a keyword argument here. And then we're going to add atoms.calc equals EMT. And then let's return atoms, comma, atoms.get potential energy. And let me also do atoms.get volume. Do I need that? We don't need that. Let's get rid of it. Okay, and now let me run it in this cell so we can have it in another cell. Then I can say get energy copper and 3.6, and that is going to give me that atoms object and this energy. Okay, so I'm going to cache this at this kind of atomic level. Every single time I run this, we're going to get a cache, and then next time I run this, it's going to look it up from the cache. I really should probably add that ka-ching sound so it's more obvious, but maybe we'll skip that today, and then we'll just check what's in the cache. Let's see, what do we have here? We do have a cache, so we have a couple of entries in it, and these are again just pickle strings, right? So it's convenient, but it's not interoperable. It's only reusable through the through Python. Okay, so the next step that I need to do is run this for a series of different values. So let's see, I'm going to try 3.5 to 3.7. So I could make an NP, I'll probably have to import NP. Let's make a linspace and go from 3.5 to 3.7 and do 10 points. And then we could say results is going to be get energy for copper, comma A for A and A. And this is going to now be a list of these atoms, objects, and energies. And then I need to make a plot of those. So let's say that the energies are going to be x1 for x in results, and volumes, we're also going to iterate over these. It's going to be x0.getVolume for x in results. All right, and then we're going to plot volumes, comma energies. Let's make a bit of b dot. And let's see how this looks. All right, so we see quite nice looking data, and I never really remember all the ASE equation of state code. So let's just Google it real quick. Equation of state. I think we could just use the simple one, SJEOS. So I'm going to say from ASE.EOS import equation of state, and then I give it the volumes and energies, and then I can save it like that. Okay, so let's see here, JP from ASE.EOS import. I don't think I need this one. This is going to use the Mernigan equation of state. That's a quite nice one. Rerun this, and there we get what that figure is. Okay, so what we can rerun this now pretty reasonably. Everything all those calculations we did are cached. I think for fun, I will say, what if I do p equals this? That still makes a plot. Let's do HashCache dot dump p equals p, and energies equal energies, and volumes equal volumes. So this is going to dump the figure. I'm not sure how usable that's going to be later, and the data, energies, and volumes, and later I should be able to look this up by that hash. So let me see what happens here. I'm going to go ahead and kill this kernel. And now we're going to try to load this and see what we get. So I killed the kernel, so I have to import HashCache again. That's going to restart. And now I need to load this. So that gives me P and the data. So I definitely could take this data and do that analysis again. That seems pretty good. Let me see what happens if I say p.show. Oh, that's an error. I have to take it from the data. That's an axes object. I wondered if there was like some way I could make it plot. Let's see. So we definitely got a Python object back. There's like update. Color, there's plot, redraw in frame. That sounds promising. If I knew Matplotlib better, then this wouldn't happen. But I'm just experimenting for fun. Not it. Get renderer. I guess I know I can add new things to it. I wonder if I should have saved the figure somehow, because this is just an axis and not an actual figure. Let's see, maybe if I make a figure I can try to add an axis, but that's not going to do what I want. Maybe we can try this. I'll make a figure, plot.figure, and then try to append it. Seems like it could work. I don't know why you would do this, by the way. It seems like it's doing it, but it's not actually showing. Oh, that's interesting. Seems like it has some non-GUI backend. That doesn't seem right. Let's try this. Let me just restart this. Oh, I wonder if I need to import matplotlib first. Let's try that. No, that seems unusual. I don't know if it should have worked or not. What does definitely work is this. Let's see, data. That's what I looked up. I could say plot.plot. I need to get the energies. And volumes. We can definitely relook up this data and reuse it by that hash. So that's pretty convenient. Maybe the message here is don't try to be too clever saving complex Python objects and try to stick to simple data structures, numbers, strings, lists, arrays, etc. Maybe there's a way to reuse that figure that I saved and then modify it and adapt it. I'm going to add cxt a to-do item here for some offline investigation. And get it to show in here. Maybe we'll try one more idea. Plot.gcf is going to give me the current figure, and I'm going to try to dump that. HashCache.dump figure equals this, and now I'm going to load it. So that's going to come from this hash. And let's just extract it. And let's see if this has a show. So, all right, so this is giving me the same thing. Maybe by virtue of loading it this way, it seems to think that matplotlib is a non-GUI backend. And it's been a while since I played with this. I know that there are ways to change this. I kind of recall that it was that it's not actually easy to change afterwards. TKAG. That doesn't really make sense to me. So that's not it. This one is surely not. I'm just trying things now that are obviously not working. Okay, so I'm not sure I can get that figure to show. Let me see what else can we do with this figure. Maybe we can save it. Get rid of this. Let's see, is there a save? Save fig maybe? Could try that. Let's see if it does. Well, let's see what happens. Let's see what this looks like. Looks like it just saved an empty figure. So I don't know what it saved in there, or what. Let me see. Let's see what else is in this. Well, it looks like that's not actually all that interesting, and it's probably going to take some effort to figure out if it's worthwhile saving a figure or not. Let me get back to what we've got here. So I have a function that I can change symbol and lattice constant. We did a couple of things where this isn't like truly automated in the sense that I had to do a bunch of pre-work, for example, to figure out the range of 3.5 to 3.7. That's certainly not going to be correct for gold. Gold has a lattice constant closer to 4.2, and so we won't even be in the minimum by that. So you have to have a little bit of pre-knowledge, which I have just by saying those words. And so this part is automated, but it isn't going to get you into the right space. We got to explore this. We did a linspace of these, and then we have this script that does the volumes and energies. So why don't we take a little bit of time now and skip past this diversion on whether we can save the figures and work on automating the whole pipeline. All right, so I think what we want to do for this is write a new function, and I'm gonna decorate this one with HashCache too. And so let's do get equation of state here. And let's just give this one symbol. So some of this is a little bit of like 20/20 hindsight, and you want to do this this kind of development on very small, very fast problems. And so the what we need to do here, I probably need to re-import this since I've restarted a few times from ase.build, import bulk. So now we're going to try to make this as robust as we can think about it. And so let me write first that A0, we're going to get the first atoms, is just going to be bulk of symbol and not specify what the lattice constant is. And I'm still going to assume, and we should document this here, that symbol is an FCC metal, and that we get an atoms object that is already in the FCC unit cell. So then we can say V0 is going to be A0.get volume. That's going to be the volume of that unit cell at the experimental lattice constant looked up from the ASE environment. And I know that the volume is equal to 1/4 A cubed. So at least if you have the primitive unit cell. And so we can say that the lattice constant 0 is going to be V0 raised to the 1/3, and then we multiply that by 4, and let's print LC0. Actually, let's not cache this just yet while we work this out. And let's check out what EOS here is for copper. It should be about 3.6, and it's not. Oh, we should multiply V0 by 4 first. I think that gives us 3.61. Okay, so that's the right idea. Okay, so that's what the experimental lattice constant is, and now we should look at a range that is plus or minus, say, 10% of that. And so now let me make a linspace that is, say, from 0.9 times LC0 to 1.1 times LC0 and let's do 10 points in that range. And these are not going to be necessarily like easy to write down lattice constants. They'll have many decimals, so it's not going to be like 3.5, 3.55, 3.6. It's going to be a whole bunch of them, but that's okay, because we don't need to print these. We just need them to be reliably reproduced. So this is going to go from 90% to 110% of that experimental lattice constant for 10 points. Then we're going to say, let's make our list of atoms. I'll do a list comprehension here. So we're going to do bulk, symbol, A equals A for A in A. All right, that's going to give me a list of atoms objects. And now I need to set a calculator on each one. And so I'm going to do that by side effect, atoms.calc equals EMT for atoms in atoms. That's going to just work by side effect, so it's a one-line for loop. Then I can write here volumes is equal to atoms.get volume for atoms in atoms. And I mix the cases here so that all caps implies it's a list, and lowercase is not. This is a place where parallelization could come to help you, but that is a topic for another day. And we're only doing 10, and it's going to run fine. And now we could say just return volumes and energies if we want to stick with simple data. But maybe we shouldn't call this get equation of state then. So I'm going to go ahead and say EOS equals equation of state, volumes, energies, and then we're going to return volumes, energies, equation of state.fit. Actually, I feel like we should just return the volume and energies and not do this here. And so maybe we'll just say get volume energies as the name of this. That way we can separate these, and in another function we can do the actual equation of state. Okay, so this is there's a couple of decisions I made in here. So this 10, for example, you might consider having that as, let's go ahead and do it. Let's say n equals 10 here, and that way you can decide what the points are. And then these are also decisions that you might want to make and not hard code them. So let's say we want 10 points. LF is going to be 0.9 and upper F is going to be 1.1, and let's change these to LF and UF. This again comes from experience of what happens if the plus or minus 10% doesn't contain the minimum. Then you're going to want to rerun this with another set of data points. You might even want to make the A here be the argument that goes in, because here we're constructing it, and if you change LF or UF, you're probably going to get n new points, and you don't need necessarily new points. You may want to accumulate the points because you might only want to do them in a particular area. All right, I'm going to change this totally. Let's get rid of these three things and just have this be A. That means we have to compute this outside of the function, and that is perfectly fine. Okay, so let's go through this again. We want to get our volumes. No, I don't want to do that because I use this LC0 down here as part of the calculation. All right, we're going to go back to this. This is a lot of trial and error, and eventually you will find something that works. It may only work for this purpose. All right, so we're going to have a symbol. We say how many points we want. We should put a doc string here. Since I'm doing this live, my doc string is not going to be super good. And with HashCache, we can change the doc string and it should not break the cache. But of course you should test that. And normally you want these to be not changed after the fact. Anything we change in here will certainly have an impact. Okay, so here, if I run this, get equation of state. Oh, I cannot run that as a list comprehension. So we do have to make a for loop here. I think there might be another set calculator option that would have worked for that, but oh, and I changed this so you can see, you know, it's a challenge that even though I changed the name, this is still in memory. And we still have an energy. Oh, NP is not defined. No worries. Okay, so now this works, and you can see why I'm using EMT. It's just very fast. You don't want to wait a day to find out there's an error. We have the volumes and the energies, and now it's time we can go ahead and decorate this, and we'll get to run this, and we might say volume comma E is equal to this. Say from ase.eos import equation of state. This is hashed, so I should be able to now just unpack this maybe. Let's see if it works. That's fancier than necessary. And then we should get a equation of fit. So this is going to be the minimum volume, the minimum energy, and probably something like the bulk modulus. Okay, and we could now do this for other systems as well. And let's do this for palladium. And let's do this for gold. And so you can see the volumes are bigger than this, and these should all be cached, so we should be able to just run these again if we wanted to combine them all into one plot. So let me see how let's see what is in here. So equation, we can set an axis. So we might even be able to combine these. I think I probably should have said, made this equation of state 1, equation of state 2. Since these are cached, it's pretty straightforward to change these. Oh, and now let's make this one 0. And let me say EOS plot somehow I really have messed up my matplotlib. Let me see if I restart here, if that goes away. Not, oh. All right, there we have our three plots. I don't love this plot. They're all the same color. It's hard to tell what's what. Even if I add a legend, something is not quite right, and so we would need to do some work in differentiating these. Do I even need show here? We don't, but that allows me to kind of look up this data and reuse it after the fact. So I'm going to finish up here, and we can see in this case we were able to automate this to a large degree, where we have a function that takes the chemical element, does this. We did not do anything fancy in terms of checking that the minimum is in the range. That's something we probably should do, and because it's not always the case, and it does seem like we would need to be able to look at other ways of doing this plot. For example, we could simply have, let's do this, plot. Palladium. Here's a way we can reuse the data more effectively, and I don't know why it jumps to these images sometimes. is interesting with EMT. It sort of puts the minimum near zero for all of them, and then we can individually extract out these analyses. Anyway, that's going to be it for today. This was a exercise in using the electronic notebook for simulation data, and we'll probably come back to it another day for something more sophisticated, but hopefully we'll get some other kinds of experiments in here where we can investigate this. So that's all for today. Thanks for coming.